and how it is being utilized is all is being comprised in unit 1 under subdivisions called as evolution, elements, the important concept TIR, total interreflection, the numerical aperture, optical fiber modes, mode theory of circular waveguides, overview of model key concepts, LP modes, linearly polarized modes. What we're going to see in unit number 2 is we're going to see the degradation of the optical fibers. So we have when a signal is being transmitted from a source to destination, it undergoes different changes. So as we send 100 watts of power as a signal from a source to a destination, not all the 100 watts of power is being delivered at the receiver. So due to the environmental factors, due to the Yeah, in unit number 2, we'll be addressing the different losses that occurs during the usage of an optical fiber cables. So the losses are, for example, attenuation, absorption, scattering, bending, co-cladding, how they occur, why they occur, what are the reasons, how to rectify them. Then the next degradation is distortion due to the optical waveguides nature. Then we'll be seeing the group delays, then a different type of degradation, which is dispersion in terms of material, in terms of waveguide. Then we'll be seeing the signal distortions in single mode fibers, SM. SM represents single mode. And in GI, it is graded index fibers. So the design towards the single mode fibers with refractive index profile and its cutoff wavelength. So all these things in terms of losses and rectifying them is what we are going to see in unit number 2, degradation of optical fibers. In unit 3, we are going to see the sources. What are the different types of optical sources available, how they are working, what are the different types like LED and lasers, how they work, in what mode does the LED supports, what mode does the laser supports. LED supports your multi-mode, laser supports your single mode. So there's all these two different structures and their types with its equivalent external quantum efficiencies, resonant frequencies, and the type of sourcing to external is what you are going to see in unit 3's first half. Then the coupling. So we will be having couplers to join one fiber with another fiber by using the power launching and coupling schemes, especially lensing schemes. So this joining of fibers can be done by fiber to fiber joints and disjoints. We have butt joint, we have V joint. Then cutting and rejoining of optical fibers, we call it as fiber splicing. So that we are going to see with its detection response time. So all the optical sources and couplers we are going to see in unit number 3. So in unit number 4, we will be seeing the fiber optic receiver. What is the fundamental receiver operation? How it is being operated? What are the different types? How to receive a signal which is fiber optic in nature? How to convert back into electrical signal? Then pre-amplifiers, the error sources that are being generated due to that, the probabilities of errors being occurring, then the measurement of attenuation, which we had seen in unit number 2, how to measure what are the techniques being used for measuring attenuation, for measuring dispersion, how to measure refractive index, or how to find refractive index of optical fiber, how to find the cutoff wavelength of optical fiber, how to determine the numerical aperture of a cable which is being given, and then how to find the fiber diameter measurements. So all this in terms of theoretical aspects we'll be seeing in unit number 4's second half, and the measurement of them in practice we are going to do it in laboratory. So then unit 5, it is optical networks, the high speed transmission of optical signals from one place to another place with the help of improvised technologies in terms of networking. where we'll be using synchronous optical networks, synchronous digital hierarchy, or the wavelength division multiplexing networks with wavelength routed networking. So for this, link power budgets, rise time power budgets, the effects of noise on the system, the operation of wavelength division multiplexing, its performances, the principles, along with EDFA. So EDFA is erbium doped fiber amplifier, which are specific amplifier which are used in modern sonnets or solitons that are used for high data rate transmission. Then at last we'll be seeing some specific topics, which is optical CDMA and ultra high capacity networks that are used in optical networking. So at last, at the end of the course, you'll be able to understand the optical fiber communication link. We'll be able to demonstrate how to do that. We'll be able to determine the structure, the propagation, transmission properties of an optical fiber. You can easily understand how to find it. You can easily estimate the losses analysis of the propagation characteristics of an optical signal. You can describe the principles of optical sources and power launch coupling methods. You'll be able to compare the characteristics of fiber optic receivers, which receiver is best in which different case, and at last you can able to design an fiber optic link based on budgets, such that you can improve the capacity of the system in terms of minimizing your errors or increasing the data rate. You will get an clear exposure towards these 5 different points when you understand this optical communication. And I will be helping you in understanding all these concepts through the way of PowerPoint presentation, through videos, through lectures, and in turn you will be learning with the help of tutorials, practices, laboratory sessions, followed by adequate knowledge gaining system called as tests, assignments, MCQs, or even discussion in chat box, billboards will be done. So this is what the introduction about optical communication is. So at the end of the course, you'll be able to know where this optical communication is being used. What are the different applications? In which of the places we are using optical links? How it plays a major role in today's scenario, and how it will play in future also. So if you have any queries, you can type in chat box. If you have any queries, type in chat box. So another 2 or 3 minutes, I'll give you time for a breathing time. If you have any queries, you can type in chat box. Then I'll proceed on to unit number 1. Okay, since there are no queries, thank you Sai Kirtan, thank you Mukesh, thank you Sri Vishnu for your feedback. That's that you don't have any queries. So first of all, before starting unit 1, I would like to introduce as how this optical fibers are being made. Okay, since we're dealing with fibers, optical fibers and its communication, first we need to know how they are being made. So then it will be easier for you to know how this works out. Okay. So first of all, I'll be showing you a small video on how the optical fibers are being manufactured or fabricated. Okay. So let us see that. Then we'll move on to the introduction to unit 1. Yeah, you are able to see this?
Yes, sir.
Just I'll play it.
Every time you talk on the phone or go on the internet, what you say or type travels to its destination through fiber optics. Voice and data gets transmitted via pulses of light through hair-thin glass fibers. Those fibers start out as large glass tubes. First, workers unwrap the tubes.
These are your fibers with different refractive indexes.
Then they submerge them in a corrosive bath of hydrofluoric acid that removes any oil residues. Then they set a tube into each end of a lathe. As the tubes spin, they're heated with a hydrogen-oxygen flame. When the glass turns white, it's getting close to hitting peak temperature. At about 3,500 degrees, the two tubes fuse together. They put this new longer tube onto another lathe. As the tube spins, they inject a mixture of chemical gases inside, while a traversing burner heats everything up. The gas mixture contains liquid forms of silicon, an abundant chemical element found in nature, and germanium, a chemical element similar to tin that's used as a semiconductor in transistors and other electronic devices. As the gases heat, they undergo a chemical reaction that leaves a white soot on the inside of the glass tube. The heat fuses the soot, forming what will eventually become the core of the optical fiber. The glass tube itself will form the fiber's covering. When there's enough fused soot, they turn up the heat until the soot itself turns into glass. Then they heat the glass tube enough to soften it, and to soften the new glass inside. The intense heat eventually makes the tube collapse on itself to form a solid rod. The internal structure of the optical fiber has been achieved. But it's in the form of a big bulky rod called a preform. So the next step is to thin it out. First, they excise the preform from the uncollapsed section of the glass tube. Then they install it vertically into the drawing tower, which will draw out the final shape. The drawing tower's oven heats one end of the preform like honey dripping from a spoon. Then, using a glob of glass as a weight, they stretch the soft glass and keep stretching it until they formed a thin glass fiber. A series of pulleys measure the tension on the fiber as it's being drawn. A special monitor makes sure the fiber is precisely the right diameter, just 5/1000ths of an inch. Then the fiber passes through UV lamps that bake on an acrylic coating to protect against dust and other contaminants. Finally, the fiber is rolled onto a drum. From here, it's either shipped out as is or put into a cable. Fiber optic cables are expensive to produce, but they're smaller and lighter than traditional copper cables. They carry more information and need fewer repeaters to keep the signal from deteriorating. And unlike copper cables, they're immune to electromagnetic interference. They're also hard to tap without being detected. And all of this is made possible by a complicated process based on a very simple principle: light traveling through glass.
Yeah, I hope you would have seen two videos that illustrates how optical fibers are being fabricated. So the fabrication is done by taking the molten. It is made up of glass, fiber glasses. So they are being heated up around 1200 degrees Celsius. They are heated, which may have the same refractive index or different refractive indexes. They are being mapped together or coupled together into same. Then they are put up in the drawing furnace, as you have seen. So the first droplet that comes out, when the person pulls it down, it goes into a larger tube-like tube-like structure. Then that is being put on as the perform. So that perform after a certain period of time, when it reaches to the bottom of the machine, they cut it or they discard it, and they fix an leveler such that the appropriate diameter size which the manufacturer requires, which varies from 125 micrometers. Keep in mind micrometers, the dimension of the fiber. With respect to core cladding, that they fix it, and this perform runs from the top and gives us optical fiber. So this optical fiber is used in mainly in communication purposes, in networking, and in the desired places of transmission of signals. So the best example where we use the optical cable is that if you do possess a PC, if you do possess a laptop with mouse. So nowadays all are optical based. So optical based mouses being available. So during the evolution of the PCs, they used only ball type mouses. So you'd be having an uh, ball like structures inside the mouse. So depending upon the roll or movement of the mouse, the signals will be transmitted. Now and all, we have an LED being fixed inside the mouses. So just when you as you move or as you drag it, so depending upon the reflections of light being present, so that is being moved out. So best example is that in mouses that we use in a PC or laptops, or even in mobile phones or tabs that we use, the reflections that we do on this touch screen is being all done by the optical pulses or the optical data that are being sent. So I'll give you some 3 to 4 minutes of break. If you have any queries, you type in chat box. Then I'll start the optical unit 1 session. So queries, put in chat box. Yeah, since no queries, so move on to the introduction. Okay. So, optical fiber communications, Unit 1, Introduction to Optical Fibers. So Unit 1 is fully introduction. So what are the contents in this presentation is that first we'll be seeing evolution of fiber optics, the elements present in the fiber optic transmission, the ray optics, the optical fiber modes, single mode fiber, multi-mode fiber, step index configuration, graded index configuration we are going to see. Then the linearly polarized modes, and specifically we'll be seeing a single mode graded index fiber structure. First of all, I'll introduce this optical fiber to you. So what is an optical fiber? Is that it is a thin, flexible, transparent fiber. Okay, optical fiber is a thin, a flexible. When you bend the fibers, it will bend. When you try to make a subtler hue of the fiber, it will do. When you push through, it will get pushed. When you pull through, it will get pulled. So flexible. It's transparent, means at one end of the fiber, when you transmit a light signal, at the other end it will transmit as it is without any absorption. So that is what transparent. So that will act as a waveguide. That acts as a waveguide or light pipe. Seen a light pipe? A pipe with a hole. When you pass light through one end of the pipe, the other side you will be able to retrieve it. Okay, so that is what a optical fiber is, so which is used for transmitting light between two ends of the fiber. So simple, optical fiber is a thin, flexible, transparent fiber acting as a waveguide or a light pipe for transmission of light between two ends of the fiber. That's all. So where can we use this thin, flexible, transparent fibers that acts as a waveguides? They can be used in fiber optic communication that permits transmission over longer distances with higher data rate. So why do we use this? And instead of, why don't we use a metal fibers, or why don't we use metallic wires or existing cables? Is that if you use an optical fiber instead of all the existing electromagnetic based metallic wire structures, we can use it because the signals travel along the fibers will have lesser loss compared to the electromagnetic wave transmission on the cables or on the transmission lines. The optical fiber cables will have lesser loss, and when we use an electromagnetic wave radiation, the electromagnetic interference is also more. So when we use an optical fiber in the place of an electrical cable or wired cable, the electromagnetic interference which is occurring can be minimized. So this is the reason why we go for an optical fibers. So what is the evolution of this? So evolution means the history of optical fiber system, how it came into existence. So which has been divided into three generations. Okay, the fiber optic system. So the first generation used GaAs, which is gallium arsenide semiconductor lasers. So laser is a type of source, optical source. So that we'll discuss in depth in unit number 3, how it works. So for the time being, what was used in the first generation? We're going to see. So the first generation of lightweight optical communication system used gallium arsenide semiconductors operating at zero point 0.8 micrometer. So keep in remembrance, micro represents 10 power minus 3. So this generation gave a bitrate of 45 megabits per second, mbps, where for every 10 kilometer there was a repeating station. Every 10 kilometer there was a repeater station being deployed, repeating the signals. Next, next came the second generation. The bitrate, which was only 45 megabits per second in first generation, was evolved and it was upgraded to 100 megabits per second to 1.7 gigabits per second. Minimum bitrate was 100 megabits per second to 1.7 gigabits per second. Of information was being transmitted from source to destination with a repeater spacing of 50 kilometers. So in first generation, for every 10 kilometers of distance, I need to keep repeaters, optical repeaters. So whereas in second generation, I need to keep only at 50 kilometers. So which is 5 times savings. If I want to place a repeater station at every 10 kilometer, for example, assume 100 rupees is the charge. So for 50 kilometers, I need to give 50 rupees. But when we deploy the second, when it was deployed in second generation, it was 1/5 of that. So which is for every repeater station, the deployment was at 50 kilometers. And the operating wavelength was at 1.3 micrometer. And the semiconductors that was used is that INGA-ASP, indium gallium arsenide phosphide. So this was being used in the second generation. Then in the third generation, the bitrate was again increased to 10 gigabits per second with a repeater station repeating at every 100 kilometers. And the operating wavelength was also being increased to achieve this data rate at 1.55 micrometers. So using the same semiconductor material as used in second generation. Next was the fourth generation. So in fourth generation, WDM technique was introduced, wavelength division multiplexing, where bit rate shoot up to 10 terabit per second. Keep in mind terabit. Then repeaters only for every 10,000 kilometers and operating wavelength at 1.45 to 1.62 micrometers. Then in the fifth generation, the Roman amplification technique and the optical solitons made the optical fiber communication to reach 40 to 160 gigabits per seconds of data rate, with repeaters being repeated for every 25,000 kilometers to 35,000 kilometers. So one repeater station is necessary for every 24,000 kilometers. So the operating wavelength was around 1.53 to 1.57 micrometer. So there are 5 generations of optical fibers. So, and depending upon the application and need, we'll be using this, and depending upon the cost, deployment cost also, we use the different any one of these 5 generations models. Okay. So now let us see the elements of an optical fiber transmission link. So what an optical fiber transmission link will have. So it's a simple, as we see in a communication, we have 3 different important blocks. One is a transmitter, second one receiver, and in between the receiver and the transmitter we have a channel. So that is what same here. Okay. A transmitter which will be having source, then we have a channel where the information that have been transmitted is to be carried out to the receiver. So this is a block diagram of the optical fiber communication system. So we have a message, original message as either text, audio, video, JPEG, JPEG, whatever might be. So they are being processed by using an appropriate modulator. It is given to a carrier, then to the channel coupler at your transmitter section. So at your transmitter section, we'll be having a channel coupler which will have the optical sources. So depending upon the variations of the electromagnetic signals received to the optical source, they will emit light signals. So that are being coupled into the optical fiber links. So here from the channel coupler to the repeater, and then from repeater to the optical detector is all made up of optical fiber cable. So the region between the transmitter and the receiver is called as information channel, as we all are familiar. So then the signals that are being transmitted from the sources are being repeated, passed on to the optical fiber cables, then it reaches the receiver. So at receiver, appropriate detectors are being used, optical detectors we call, which convert the light signal into electric signal. So then they are being given to amplification circuits, then they are being processed, and the original message signal that we are transmitted at the transmitter is being retrieved at your receiver. So message input, message output. So this is the block diagram. Light beam pulses are fed to amplifier, are fed to fiber optic cable. Then they are transmitted over longer distances. At receiving end, light sensitive devices, the detectors are being used to detect the light pulses. So these detectors will convert the light pulses into electrical signal. Then these pulses or signals are amplified or shaped back to digital form. So what does this fiber cable consists of? The fiber cable consists of 4 main parts. First one is the inner core. Second one the outer cladding. Surrounding the cladding we have the buffer, then that surrounding the buffer we have a jacket. Here in this diagram you can see the core, the four main parts of the optical fiber cable. Core inner, surrounding the core we have cladding, surrounding the cladding we have buffer, surrounding the buffer we have a jacket. So here a dimension is given for core, 8 micrometer, which is the diameter measurement. 125 micrometer is the cladding diameter. 250 micrometer is buffer diameter. Jacket 400 micrometer diameter. So this is the structure of fiber optic cable. So now let us see what is the function of each and every core, cladding, buffer and jacket. Each and every part's function. The core, which is the inner part of the fiber cable, is a cylinder of plastic that will run all along the fiber's cable length. Only in this core, the light will travel. The diameter of this core will vary depending upon the application that we are going to use. And most probably the core dimension or the core cross section should be always circular for most of its applications. Due to the internal reflection, the light will travel within the core and it will reflect from the core from the cladding boundary. So this means that the core and cladding will be having different refractive indexes values such that the light traveling through the core will move on to the receiver side by a principle called TIR, total internal reflection, that you are going to see in the subsequent slides. So there will be different refractive index for core and cladding. So next is the second part, which is cladding. So cladding is an outer optical material that protects the core. The main function of the cladding is that it reflects light back into the core. Okay, reflection principle is done by cladding material. So when light enters through the core, which is having a denser medium, into the cladding material, which is having lesser denser material, its angle changes. Its angle changes and reflects back to the core. This is the function of cladding. When light enters through the core, which is a denser material, to the cladding which is having lesser denser material, the angle of the light will change, thereby making a reflection back into the core. So this is where total internal reflection principle comes into play. So next part of the immediate layer that is present after the cladding is your buffer. The buffer is used to protect the fiber from damage of cladding and core. This protects thousands of optical fibers arranged in hundreds of optical cables. So each core and cladding which are being present will be arranged in a fashion inside a single optical cable. So these bundles which protects the core and cladding are protected by the outer covering called as jacket. Okay, so this is a fiber optic cable. Core cladding buffer jacket. So the jackets are available in different colors that are used. There are different colors being used for jackets, where some colors we can able to identify what they are meant for. The outer jacket is yellow color. It indicates it is used only for single mode cables. If it is orange, it should be used only for multi-mode. So these jackets provide this type of information, whether the cable is meant for single mode or multi-mode. Next is characteristics of fiber. So there are three different types of characteristics that we need to see for an optical fiber. Is that one is the bandwidth, the optical carrier frequency for the fibers is 10 power 13 to 10 power 15 hertz with a low transmission loss of 0.002 decibels per kilometer. Then the dielectric waveguide is to be considered. So the optical fibers are made from silica, which is electrical insulator. So therefore, they do not pick up any electromagnetic wave or any high current lightning. So as shown in the video, I had shown you a molten which is being heated up, and that gives a resultant glass fiber like structures where we send the optical waves. So that molten that we heat it up is purely silica, which is an electrical insulator. Next characteristic is the signal security. The transmitted signal through the fiber does not radiate at all. Means that neither of the glass material, nor the cladding, nor the fiber, nor the jacket absorbs radiation of the signals, optical signals. So further, these signals cannot be tapped easily. Next characteristic is that small size and weight. The optical fiber cables are developed with small radius and they are flexible, compact, lightweighted. They can be bent since they are flexible. They can be twisted without any damages also. So these are the 5 different characteristics. Mm. Okay, okay, Mukesh. Move on to the next slide. After the characteristics of fiber, operation of the fiber. So how does this optical fiber works? As defined, a fiber is an hair or a thin fiber structure which consists of two layers, the core and the cladding. Then it is surrounded by the protective sheets. Okay. The core and cladding will always have different refractive indexes, where the refractive index of core is given as N1, which is slightly higher than that of the refractive index of the cladding, defined by N2. So core refractive index N1, cladding refractive index N2, and N1 is greater than N2 always. Refractive index of core is slightly higher than refractive index of cladding N2. Then this difference in the refractive indexes enables the fiber to guide the light to move from one end of the fiber to the other end of the fiber. It is this difference that in refractive indexes of the core and cladding makes the fiber to guide the light to move from one end to the other end. So because of this guiding property, the fiber is also referred, referred to as an optical waveguide. Thus the name optical waveguide is given to optical fibers. So let us see the advantages. There are 5 advantages of the optical fibers. First one, the characteristics of light that is emitted from the source is measured in nanometers. So the measurement of wavelength in terms of nanometer is very much easier. Nano is 10 power minus 9. Then the frequency of operation. It is the number of pulse per second emitted from a light source, which is equivalent to 1 unit hertz. So 1 hertz will be equal to 1 pulse per second. So for every second, if 1 pulse is moving, it is equivalent to 1 hertz. Third advantage is that the optical fiber are confined to narrow windows, which is defined as the range of wavelengths at which a fiber operates at its best. So narrow window. So we have seen that window of 1.43 to 1.57 in the fourth generation, I think so. In the fifth generation, 1.52 to 1.57 in the fifth generation. So those are the narrow windows. The narrow windows of wavelength of operation gives best operation, means that higher data rate. The next advantage is that lower attenuation as compared to electrical wires or electrical cables. Attenuation of optical fiber is caused by intrinsic factors, primarily scattering, absorption, and extrinsic factors. Those are the manufacturing defects, the environments, and the physical bending. So those are very, very less. Next is the dispersion. So dispersion is the spreading of light pulse as it travels down the length of the optical fiber. The dispersion limits the bandwidth or information carrying capacity of the fiber. So this dispersion is also very lesser as compared to electrical cables or wires or the metallic wires. And there are some Disadvantages in the usage of optical fibers. The first one is the deployment of cost. You need to invest more and more money by deploying optical fiber. The transmitters and receivers are very much expensive depending upon the application. The jointing splicing techniques are more difficult. The price is very high. Fragility is the main factor. When it is exposed to chemicals, they easily get destroyed. Opaqueness is another disadvantage. Then in order to maintain and in order to restructure or work on the fibers requires some special training. These are the disadvantages of using an optical fiber. So depending upon the need and request, the optical fiber can be deployed as per the requirements.